Hey everyone, welcome to Sources Classes. So let us solve a question. Um, Here, the question in front of you is asked about Leontief inverse matrix. Okay, so this is a question from mathematical economics. So what is the Leontief inverse matrix? First of all, that is the question, and the next they have asked you to highlight the properties of it. Okay, of this matrix. So let us first define what this Leontief inverse matrix is. So basically, this matrix is used to model the interdependence of sectors in an economy. Means like suppose if we have two sectors and two commodities are produced X1 and X2, then here we try to study the dependence of industry 1 on industry 2, and again dependence of industry 2 on industry 1. Means if X1 is produced, that will be needed to produce X2, and if X2 is produced, that will be needed to produce X1. So what is the dependence? In order to study that, we have to know about the Leontief inverse matrix. Now it is defined as the inverse of the Leontief input-output matrix. So what is the meaning of input-output matrix? So as I told you, if there are two industries and they are producing two output, X1 and X2, so that is the output. Now in order to produce that output, the other output is used as input. That means if you want to produce X1, then X2 will be used as input. Again, if you want to produce X2, then X1 will be used to produce X1. That means when X2 is the output, 1 is input. When X1 is the output, 2 is input. So that means both of them are input and output, and that combination is the input output matrix. So what I'm trying to tell you is, if there is X1 and X2, then suppose A11. What is A11? A11 means in order to produce 1 unit of X1 output, how much X1 is required as input. Again, if I write A12, it means in order to produce 1 unit of X2, how much X1 is used as input. So these two shows X1 is used as input to produce X1 and X2 respectively, right? So that is why these type of matrix is made of input and output. These are output, this is input and output matrices. That is what we mean by input output matrix. Similarly, if we write down A21, then A21 is going to be, 2 is going to be the input and 1 is going to be the output, and hence the name is given as the input output matrix. So this matrix basically shows, this input output matrix basically shows the input requirements of each sector in the economy to produce 1 unit of output. So as I explained, if we write it down like this, that is Aij is equals to ith input for 1 unit of xj output. Okay, so this is the meaning. Now in economics, this Leontief inverse matrix is used for the, first of all, as we said, as we just studied, that is analysis of input output models, so that the demand and supply change can be determined in various sectors of the economy. And secondly, it can also be used to calculate the multiplier effect of government spending, investment in the economy. So these are the purpose or economic application of using Leontief inverse matrix. Okay, now what are the properties of this type of inverse matrix? So we will just quickly note it down. So number one, this is a square matrix. Number one, this is a square matrix, non-negative matrix, number three is it is a unique matrix, and of course inverse is mentioned in the name itself, so the fourth one I can say is inverse matrix. So these are the 4 properties of Leontief inverse matrix properties. Now let's move on to the next part of the question. There is another part of the question, that is, consider the Leontief input coefficient matrix. Okay, so this is the input coefficient matrix that is given. Now, test the viability condition of the system. Now, how can we test the viability condition of the system in this type of maths is through Hawkins-Simon condition. So, if a system of input coefficient matrix satisfies Hawkins-Simon condition, then that means viability condition of the whole system is verified. Now, how can I verify this viability, or how can I satisfy Hawkins-Simon condition? Now, Hawkins-Simon condition needs two factors. Okay, what are it? What are they? So for that, what is the problem imposed by the economy? The answer to that is the Hawkins-Simon condition, right? So we know that total output produced in the economy, X1, right? So this is consumed by the buyers as well as by the producers in terms of inputs. So let us write down the equation of X1 as 1 minus A22 by delta C1 plus A12 by delta C2, and X2 is equals to A21 by delta C1 plus 1 minus A11 by delta C2. So these are the two equations. Now what is the problem in the economy? The economic problem is that these consumption C1, C2, these are semi-positive. What do you mean by semi-positive? Semi-positive means C1 or C2 is positive, other one will be 0. Both are not positive. That means if this is 0, this is positive. If this is 0, then this is positive. This one among these two is going to be 0 and the other one is positive. So this is called semi-positive. Now the problem in the economy is, if the consumption is semi-positive, how can the demand X1 and X2 will always remain positive? Means if either of C1 or C2 is 0, then how can always X1 and X2 be positive? That is the question. Now that means I need to find out such condition where even if C1 and C2, either of them is 0, X1 and X2 will always be positive. And those conditions are called the Hawkins-Simon conditions. So let us write down the conditions. So this is very clear from this output system that, let me suppose C1 is equals to 0, then obviously C2 is positive. So from X1 it is clear that if C1 is equals to 0 and C2 is positive, so A1 by 2 by delta, this should be positive for X1 to be positive. So A12 should be positive and delta should be positive. Again, if we reverse the condition, that means if C2 is equals to 0 and C1 is positive, then the reverse is the condition, that is delta is obviously that is needed to be positive. Another one is 1 minus A22 should be greater than 0. That means in order for X1 and X2 to be positive always, X1 and X2 to be always positive, these coefficients, these are the input output coefficients, should be always positive. So our viable conditions that satisfies Hawkins-Simon conditions, which will show that our system is viable, are: number 1 is A12 should be greater than 0. Number 2 is A21 should be greater than 0. Or number 3 is 1 minus A11 greater than 0. And 4 is 1 minus A22 greater than 0. Apart from these, you need delta to be greater than 0. So all these should be independently positive in order to make X1 and X2 always positive, no matter if any of the consumption is 0. So this is our viability condition on, let's say, Hawkins-Simon condition. So now the coefficient matrix that is that we are given, let us write it down. So we are only given the input matrix, so we have to write down the I minus A, that is the input output matrix. Okay, that delta is equals to I minus A. So I need I minus A determinant. Now first let me write down the A matrix, that is the input matrix. What is the input matrix again? Let us go up and write down. So we have 0 0.2, 0 0.1, 0 0.2, 0 0.3. 0.1, 0.2, 0.3, 0.2, 0.2. What else do we have? Let's check. Yes, 0.4, 0.1, 0.6. 0.4, 0.1, 0.1 and 0.6. So this is our input matrix given. Now the first step is to find out the input output matrix, that is I minus A, right? So let us find out I minus A. I minus A is equals to I will be 1 0 0 0 1 0 0 0 1 minus A matrix is our 0 0.1 0 0.2 0 0.3 again 0 0.2 0 0.4 0 0.1 0 0.2 0 0.1 0 0.6. Now this is equals to 1 minus 0 0.1, so this is 0 0.9 minus 0 0.2 minus 0 0.2. Again minus 0 0.2, 1 minus 0 0.4 is 0 0.6, again minus 0 0.1. Then minus 0 0.3, again minus 0 0.1, and finally it is 0 0.4. So this is our I minus A matrix or delta matrix. Now from here, let us calculate the matrix, that is 0.9 into 0.6 into 0.4 minus of minus plus, so 0.01. Minus plus again, so 0.2, so we have minus 0.08 minus of 0.03 and again minus 0.2, that is 0.02 plus 0.18. Now if we solve this, the answer is 0.145. So from here it is clear that our first requirement, that is delta is equals to 0.145, which is positive. Next requirement is I have to check the principal minor of the same matrix. What is the principal minor of this determinant? The cornermost principal minor is 0.6 minus 0.1 minus 0.1 and 0.4. That is 0.6 minus 0.1 minus 0.1 and 0.4. So the determinant of this matrix is 0.24 minus 0.01, that is 0.23, and the second condition is also positive, so checked. First condition for viability checked, second condition for viability check. What else do we need? We need all the diagonal elements of this input output matrix to be positive. That is, I need, since this is a 3 cross 3 matrix, I have 3 diagonal elements, 1 minus A11, 1 minus A22, and 1 minus A33. So let us find out the values. We have 1 minus A11 as 0.9, right? All the diagonal values are 0.9, 0.6, 0.4. So clearly all the diagonal elements are positive. That means all the 5 conditions are satisfied. So Hawkins-Simon condition is satisfied. So viability test is successful. That's all.